Thank you for the introduction, and good afternoon, everyone. So today, I will tell you how we can detect a particular type of internet routing attack that is called forged origin BGP hijacks. But perhaps you don't know about BGP hijacks, so let's start with a quick introduction. Imagine we have a mini internet with a few autonomous systems which are interconnected using peer-to-peer or customer-to-provider relationships. And assume now that IS7 in green announces a prefix in BGP, a prefix that it owns. So there will be a BGP route that propagates through our mini internet, and all the autonomous systems will be able to reach that destination using an AS path. So the traffic is supposed to follow this path as illustrated in green here. Okay, so now imagine that there is an attacker, IS5, who hijacks this prefix. So there will be a hijack route that propagates through the mini internet. And some of the autonomous system, actually here, 1, 3, and 6, will divert the traffic to the attacker because for those autonomous systems, the path is shorter towards the attacker. Okay, so if you know about BGP hijacks, you probably know that there are defenses. So typically there are protocol extensions such as RPKI-ROV, BGP-SEC, or ASPA. Operators are also supposed to configure route filters to prevent bogus route from propagating through the internet. And finally, there are monitoring platforms that can detect BGP hijacks in near real time. Okay? The problem, though, is that today, BGP is still vulnerable to a particular type of BGP hijack that is called forged origin BGP hijack. Okay, so what is it? Well, here, the attacker actually prepends the valid origin in the AS path so that now the hijack route actually appears legitimate from a BGP standpoint. Okay? So the drawback of such an attack is that the AS path is slightly longer, so less autonomous system will divert the traffic to the attacker, but the attack will still be successful. For instance, in this case, there is still 1 and 3 that divert the traffic to the attacker, so the attack is still successful. And the problem is that the existing defenses, they're actually poorly neutralize forged origin hijacks. Why? Because the existing protocol extensions, for instance, such as RPKI+LOV, they cannot detect them because the origin is now valid. Okay? BGP-SEC, ASPA, they are not widely deployed, and they will probably take years before they are widely deployed. Route filters, they are often missing or inaccurate. And finally, monitoring platforms, they could sometimes detect them, but they could only detect them for the AS that deploys the system. So they are sort of narrowly focused. Okay, and we actually found that those attacks are actively used by hackers in practice. So for instance, here are 2 examples where hackers targeted crypto exchange platforms. In both cases, they actually managed to steal cryptocurrencies, and in both cases, they relied on a forged origin hijack. Okay, so today, I would like to introduce you a system that is called DFOH, and it's a system that can detect those hijacks on the entire internet. Okay? So the outline of this presentation is the following. First, I will show you what is the main challenge that DFOH needs to solve. Then I will explain you how its inference pipeline works. Then I will show that the inferences are accurate. And finally, I will show that DFOH is up and running and that you can start to use it today. Okay, so the main challenge of DFOH is to detect fake IS links. So why is this the main challenge? Because imagine we have a BGP vantage points. Actually, we do have those vantage points in the real internet, the one from recent route views. So we can see the BGP route that propagates through the internet, sorry. And when we look at the AS path, here, for instance, the AS path in AS1, we will see that 5 and 7, the victim and the attacker, they are consecutive in the AS path. So it's like if they are pairing directly together, but actually they are not. Okay? So this is a fake link between the victim and the attacker. Okay? And this is actually a strong sign of a forged origin hijack. Why? Because an attacker could avoid creating such a fake links. For instance, the attacker could pretend 6 and 7. Then in the AS path, we would have 5, 6, 7 consecutively, which is a path that exists in the topology. So there would be no fake link in this case. But then the AS path would be longer. So in this case, actually, the attack would be unsuccessful because none of the autonomous system would divert the traffic to the attacker. So for the attack to be successful, it's very likely that there will be a fake IS link that is created. Okay, so we actually took BGP sessions from recent route views, and we found that every day there are about 166 new links that appear, and we don't know which one are legitimate and which one are fake, okay? So the goal of DFO is to actually discriminate the fake ACE links from the real one. And this is challenging because probably most of them are actually legitimate and only a few of them are fake. Okay, so now I will explain you how the inference pipeline works. Okay, actually it relies on two ingredients. First, a domain-specific knowledge that we combine with a tailored link prediction algorithm. Okay, so this is the pipeline of our ACE links, fake ACE links inference. Okay, so there are 3 steps. First, we take the routes from RIS and route views. We look at the ACE paths. We build the ACE level topology. We maintain it over time. And we find new ACE links. This is not new. It already exists. Okay? But then, for every new ACE link, we compute a feature vector. Okay? So here we have different categories of feature. First of all, we have the topological features. Okay, so I don't have the time to go into the detail here, but basically the ACE level topology exhibits like some particular patterns. Okay, so when a new link appears, if this new link fits well into those patterns, it's a sign that it is legitimate. But instead, if the new link sort of breaks the pattern, it's a sign that it is fake. Okay. So we have 11 topological features to capture different patterns, and we use them in our inference. Then we have the peering DB features. So here, actually, DFO looks at public peering information and can identify whether 2 ASCs are supposed to peer or not. Okay, so more precisely, DFO looks at information in peering DB. It looks at the country, the public AXP, and the private peering facilities. So, of course, the data in peering DB might be missing or worse, polluted by an attacker. So what we do is we don't actually compare the peering information of the hypothetical victim and attacker, but instead we look at their neighbors. Okay, so for instance here, we will compare the peering information of 3 and 4, the neighbor of 5 and 7 respectively. And if they have very dissimilar peering information, for instance, if they are in different countries, if they connect to different XPs, or if they are in different facilities, it's a sign that 5 and 7, actually, they are not supposed to directly peer together. Okay, then we have the AS path pattern feature. Okay, so here, DFO not only look at the new link, but it looks at the entire AS path that includes the new link. And here, when we look at some of the characteristics of the autonomous systems, we are supposed to see typical patterns that are caused by the typical business relationship that ICs are supposed to follow. Okay, so for instance, when you look at the IS node degree, between 2 stubs, we are supposed to see something like this. So the degree starts very low, and then it increases because the path goes up into the hierarchy, and then it decreases. That's a legitimate pattern. Okay, this is also a legitimate pattern. It can happen between a core and a stub. So the origin has a high degree, is the stub, and then it goes down. But this is a suspicious pattern. Okay, so for instance, it could typically happen when a stub hijacks a core AS. Okay, so here the origin has a high degree. It's the victim, it's the core AS. The second AS in the AS path has a very low degree, it's the attacker, is the stub. And then there is the normal pattern again, but overall, this looks very suspicious. Okay, finally, we have the bidirectionality feature. This is not new. It's just that if a nice link is observed in both directions, it's a strong sign that the link is actually legitimate because an attacker cannot fake both directions of a link. Otherwise, there is a loop in the S-path. Okay, so those 4 features, actually, it's the first key ingredient in our inference pipeline. Why? Because we carefully selected them such that they compensate each other, okay? Because there are many possible attack scenarios in the internet. So we ensure that regardless of the attack scenario, at least one of them will work well and will enable DFO to make an accurate inference. Okay, so the last step of the pipeline is to actually make the inference. So here we follow typical approaches that are used in link prediction frameworks. So what we do is we sample a set of existing links, we sample a set of non-existent links, we compute a feature vector for each of them, and then we can train an inference model. Here we are simply using a random forest, and then we can use this model to make inferences and to classify a link as suspicious or legitimate. Okay? So there are many link prediction frameworks that exist today. Usually, for instance, they are used in social networks to say whether two users are going to connect in the future. The problem, though, is that if we just use those frameworks on the highest-level topology, it's not going to work well. Why? Because the highest-level topology actually exhibits a very strong hierarchical pattern. So there are a few tier ones at the top and many stubs at the bottom. Okay? So the problem now is that if we randomly sample non-existent links, which is often what happens in practice, we will end up with a very biased sample. Okay? This is actually a key observation. So I'm going to illustrate this with this figure. So what we did here is we clustered the autonomous systems in different categories based on their degree and their customer code size. Okay? So we have the tier ones, we have the stubs, we have the ones that are highly connected, and so on and so forth. Okay? And then we sampled a set of non-existent links. And then here I will show you the proportion of sampled links for every category. Okay? So here are the results, and you can see that if we do this, we end up with 98% of the links that actually connect to stub ASCs. Okay? So what happens if we use this sample in our training? Well, DFO will work very well in scenarios that actually involve two stub autonomous systems, but it will perform very poorly for all the other scenarios. Okay? So this is why here we're actually plugging our second key ingredient, which is a balanced sampling scheme. Okay? So we ensure to sample all types of links in the topology and use them for the training to make sure that in the end, DFO works well regardless of who is the attacker and who is the victim. Okay, so now I will show you that in fact, the inferences are accurate in every attack scenario. So it's a bit tricky to evaluate DFO because there is no grand truth at scale. So what we did is we artificially created 4 Georgian hijacks. So how we did that, we took existing IS paths, and then we just added a new link at the end. So in some cases, the new link that we added actually exists in the topology, in which case it's a legitimate case or a negative case. In some other cases, the link does not exist, in which case it's a suspicious case or a positive case. And then we can compute the true positive rate and the false positive rate. Okay, so here are the results about the true positive rate. So here, again, we are taking the different categories of autonomous system, and we compute the TPR for every possible attack scenario. So here, green means high TPR, it's good. White means low TPR, it's bad, okay? So here are the results. So you can see that it's pretty green, actually. The lowest TPR is 0.73, which is still quite high. So it means that we will not miss a lot of hijacks. We have quite a good coverage. In terms of false positive rate, so now green means high FPR, white low FPR. So we want a low FPR here. And here are the results. So you can see that regardless of the attack scenario, we always have a low false positive rate. Okay? Actually, the maximum FPR is 0.15, which is still quite low. Okay, so now I will show that DFO is up and running and actually useful for operators. Actually, DFO runs at this URL, so if you're interested, you can go on the website. We are listing all the suspicious cases that we detect. So we are listing past hijacks, but we are also running the tool in real time, so you can detect them in real time. And DFO is actually useful and practical for network operators. It's useful because, for instance, it detected the 2 known 4 Georgian hijacks that I mentioned earlier in the presentation. And it's practical because we measured that for 99.8% of the autonomous systems, DFO only reports 0 or 1 suspicious case every month. Okay, so this is a very tiny number, which allows operators to manually investigate them and take countermeasures if necessary. Okay, so that concludes my presentation. So in a nutshell, I presented you DFOH, a system that detects forward-ranging hijacks. So DFOH runs in a commodity server. It can detect hijacked on the entire internet. It is accurate in every attack scenario. It can detect past hijacks, but also works in near real time. And finally, it is robust against adversarial inputs. Thank you.